Hey guys, how's it going? So we're gonna be learning something called Euler's totient function today. I'll just give a very general description of it, and then we can do some examples. So the Euler's, I'm gonna write it down first. I call it Euler's, but either way works. Totient. Oh God, my handwriting's horrible. Function. Before we get to that, let's let me let's do something like this. Let's do a little bit of understanding, like a bit of a notation style, if you will. Uh phi of n is this is defined as the number of integers that are relatively prime to m, or no, n, sorry, relatively prime to n. So, like, for example, we have something like this. Um, for example, phi of 4 would equal 2. And the way you would do it, like, obviously n has to be a natural number or a positive integer, if you will. I didn't want to specify this, but it's because it's pretty obvious. But anyways, there you go. And here's how you can prove it. Choose all the numbers that are from 1 to 4, are between all the integers that are between 1 to 4, and check this. Is 1 relatively prime to 4? The GCD of 1 and 4 is 1, so yep, that works. 2, the great GCD of 2 and 4 is 2, not equal to 1, so that's not relatively prime. 3 and 4, the GCD is 1, so that works. And 4 and 4 is not. It's equal to 4, so it's not relatively prime. There's only two numbers that are um, like 4, only from 1 to 4, there's only two integers that are relatively prime. So yeah, we could do another one too. Let's do phi of 9 this time. Phi of 9, well, it's the same concept. Let's just write this down, 1 to 9. And yeah, like phi of 9, well, okay, let's do it like this. Phi of 9 equals 6, but I am going to yeah, let's do it like 1 and 9 um is equal to 1. Actually, I'm going to speed this up. So 2 2 is relatively prime to 9, 3 is not. The GCD of 3 and 9 is 3. 4 and 5 are. 6 is not. The GCD of 6 and 9 is 3. And the GCD of 9 and 9 is not. So 1, 2, 4, 5, 7, 8. There are 6 integers between 1 and 9 that are relatively prime to 9. So phi of 9, by conclusion, is equal to 6. And you can keep going, right? Like if you try from phi of like 1 to 12, phi of 12, it's equal to 4. But and so on and so forth. Now, I don't really need to state the obvious. The obvious problem with this method is if you had a really big number like 100,000, you're not gonna do it from like 1, 2, 3, 4, da da da, all the way to 100,000. No, you'd be here until you die, literally. And a computer could do it so much faster than you. So no, that like obviously this method would be inefficient for large numbers, but it's a nice to know. It's a nice to know thing you have for like small numbers. Yeah, just to see how it works. Luckily for you, you do not have to do that. As you may know, every number has its own unique prime factorization. And it is unique for every number. no two positive integers in the world have the same prime factorization. It's almost like a fingerprint, if you will. Just like in real life, no two humans have the same DNA type. So two people's fingerprints on Earth in the world completely different. Same thing here. No two integers will have the same prime factorization. It's unique. And like prime factorization, like I don't know, like 24 is equal to 2 cubed times 3. It's not, no other integer will have this. Like I don't know, 1001 is equal to 7 times 11 times 13. You're not going to find it anything else. 7, 11, 13 are all primes. Like just like that. Yeah, it takes some practice to know the prime factorization and all that, but you'll get there. I believe in you. I believe in you. And there's actually a formula for this. So like knowing prime factorization, here's the thing. Actually, I'm going to erase everything except for the title. I want to keep the title of Euler's totient function. Right. So there's actually a very, very, very nice formula to find how many numbers are relatively prime to n that are between 1 and n. And that's phi of n is equal to like it's equal to two things. I'll give you two formulas. One of them is n 1 n times 1 minus 1 p1 1 minus 1 over p2 dot 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 1 minus 1 over pk, like for all the primes that are involved, essentially. So like I don't know, phi of let's just do something like 50. Yeah, phi of 50 is equal to, well, first of all, 50 is equal to 2 times 5 squared. That's the unique prime factorization. So 2 and 5 are the two primes that involved in making 50. It's equal to 50 times 1 minus 1 over 2, because 2 is the first prime, times 1 minus 1 over 5. And that's the second prime. And 50 times a half times 4/5 is equal to 20. So there are 20 numbers between 1 and 50 that are relatively prime to 50. 20 positive integers, I should say. And you could just keep doing this. Now, before we go, I won't go further. I want you to keep in mind something. It doesn't matter like the power, like that the number 5 is squared. Like if you had like 125, no, or 250, if you will, like if you have 250, the formula would be the exact same. Like I know 250 is equal to, actually, you know what? Let's change a number for a better example. Phi of 500, right? Phi of 500 is also equal to also like yeah, 500 is equal to, give me a second here, is equal to 2 squared times 5 cubed, right? It's also equal to 500 times 1 minus a half, 1 minus 1 over 5. And this is equal to 200, but that doesn't really matter. The point I'm trying to illustrate is it doesn't matter 2 to the power of what number. It doesn't matter 5 to the power of what number. Like as long as 2 and 5 have been used at least once in the prime factorization of the number n, then it's used in the prime, basically. Yeah, let's do one more. So like phi of 60 is equal to, well, 60 is equal to 2 squared times 3 times 5. That's the prime factorization. And so let's see, 60, 1 minus 1 over 2, 1 minus 1 over 3, 1 minus 1 over 5, which is equal to 16. You could put this in the calculator yourself. And it's like, it doesn't matter that 2 was squared and that 3 and 5 were only used to the power of 1. They were all, 2, 3, and 5 were used at least once in the prime factorization of 60, so they fit into the totient function formula. So yeah, that's what you have here. So I'm just gonna erase these examples right here. Just give me 1 second. So like this is the first formula that you have. Now the second formula for phi of n is equal to what was it equal to again? P1 to the A1 minus 1 times P1 minus 1 dot 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 P1, P2, P3 all the way to Pk to the power of AK minus 1 times Pk minus 1. So this is the second formula you could use. And you could use those numbers I used earlier, 50, 60, and 500, and either formula is fine. I want to show you how I got the second formula though. Like, I don't really like doing proofs normally, and I try to avoid it as much as I can, unless I'm doing it for fun. But like in this case, I think I want to show you how I got the second formula. So as you know, n, like the number n is a, it has a unique prime factorization. It's P1, A1, dot, 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 PK, AK. I should have mentioned this earlier, but P1, P2, P3, and PK, like all primes, they're relatively prime to each other, right? So then like, P1, A1, phi of that is equal to P1 minus 1, and then P1 to the A1 minus 1. And then because they're all relatively prime, yeah. So yeah, these are the two formulas that you have. You could use either formula. It's completely up to you. Now, let's do an example. Here's an example you might get on your test or on a homework assignment. And it goes something like this. Find all natural numbers n such that, or where, such that phi of n is equal to, let's say, I don't know, 8. Yeah, I just chose this number. You're never going to see something like phi of n equals an odd number other than 1. I don't really want to go into the proof because I don't want to confuse you guys, but trust me that it's true. Okay, so here is how you do it. Like, first note that every NEN, NEN, or every natural number has a unique prime factorization from n equals p1 to the a1 dot 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 pk to the ak, where p1 to pk are primes, and a1 to ak are positive integers. Okay, so yeah, you'll have something like this. Then, as I showed you earlier, you could use either formula for phi of n. So then phi of n is equal to, and in this case, I'm going to say phi of n is equal to p1 a1 minus 1. So p1 to the a1 minus 1 times p1 minus 1 dot 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 pk to the ak minus 1 times pk minus 1. Okay. Now, it's pretty obvious that so it's pretty obvious that pi minus 1 will divide phi of n, right? Because like pi, like I could be 1, 2, 3, 4. I is a number between 1 to k. And like essentially it divides phi of n. Which in this case is equal to 8, because we're finding all natural numbers such that phi of n is equal to 8. So in this case, pi minus 1 is equal to 8, right? And what are the numbers that divide 8? Well, then pi minus 1 is equal to 1, 2, 4, and 8, because these are the four numbers that divide 8. So then we can add 1 to each because we want to isolate pi by itself. So pi is equal to 2, 3, 5, and 9. But it's not equal to 9 because 9 is not a prime. 9 is equal to 3 squared, so it's not a prime. So pi is equal to 2, 3, and or 5. Therefore, we have the fact that, because remember here, like the unique prime factorization, n is equal to p1 to the a1 dot 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 times pk to the ak. Therefore, n is equal to 2 to the a times 3 to the b times 5 to the c, where a, b, and c are all natural numbers. Okay, a, b, and c are all natural numbers. Now, this part gets a little tedious, but I'm gonna breeze through it and and I'll explain each part step by step. You want to consider all possible cases, like maybe one of these A, B, or C's are 0, maybe all of them are 0, maybe 2 of them are 0. You have to go through it one by one. There's really no shortcut to this next part, so it's kind of just grunt work. There are gonna be like 8 cases here. I shouldn't have said that last part. I did this question before, so that's how I know there are 8 cases, but let's just go through them all. Case 1, here's how you do it. Okay, so the case 1 is if A, B, and C are all equal to 0. Well, if A, B, and C are all equal to 0, I'm going to box this part because we're going to refer to this for the rest of the question. 2A, 3B, 5C. Then n is essentially equal to 1. Then phi of 1 is equal to 1, not equal to 8. So this doesn't work. Case 1 is not valid. Case 2 is, now let's just consider if B and C were equal to 0 and if n equals 2a, 2 to the power of a. Well, if n is equal to 2 to the power of a, then don't forget our formula here, Euler's totient function. We have b of n is equal to 2 to the a minus 1 times 2 minus 1. That's just equal to 1, which is equal to 8. So yeah, 2 to the a minus 1 is equal to 8. 8 is 2 cubed. So a minus 1 is 3, a is equal to 4. N is equal to 2 to the power of a is 4, so that means n is equal to 16. We found a possible solution. 16 is equal to 2 to the 4, right? Phi of 16 is equal to phi of 2 to the power of 4, which is equal to 16. 2 is the only prime involved, so it's just 16 times 1 minus a half, and that's 8. So yeah, that works. Yeah, that works. Let's do case 3. N is equal to, I might run out of space here. Let's make do with what we have for now. N is equal to 3 to the power of b. Okay, well then phi of n is equal to 3 to the b minus 1 times 3 minus 1, which is 8. 3 minus 1 is 2, so dividing both sides by 2, you get 3 to the b minus 1 is equal to 4, but that's 2 squared. This is the unique prime factorization for 4. These don't match, so there's no integer solutions for b. Case 4. Oh god, I might run out of space here. Case 4 is n is equal to 5 to the power of c. B of n is equal to, using totient function, 5 to the c minus 1 times 5 minus 1, which is 8. 5 minus 1 is 4, so dividing both sides by 4, you get 5 to the c minus 1 is equal to 2. Again, no integer solutions exist for c. Okay, so case 5. Case 5 goes something like this. Now we've considered if they were all 0, and we've considered them individually. Now, the fifth possible case is if n is equal to 2 to the a and 3 to the b. Imagine if c was equal to 0. So then phi of n is equal to 2 to the a minus 1, 2 minus 1, times 3 to the b minus 1, 3 minus 1, which is equal to 8. So then this is just equal to 1. 3 minus 1 is 2. Divide both sides by 2. You get 2 to the a minus 1, 3 to the b minus 1 is equal to 4, which is equal to 2 squared. You can also say times 3 to the 0. And based on this, a is equal to 3 and b is equal to 1. And plugging this into n, you have n equals 24. And phi of 24 is equal to 8. Like phi of 24 is equal to 24, 1 minus a half times 1 minus a third, which is 8. So yeah, that works. Can I fit in these last 3 steps? You know what? I'm just gonna give you the rest of the cases. So n is equal to 2 to the A times 5 to the C. Phi of n is equal to 2 to the A minus 1, 2 minus 1 times 5 to the C minus 1, 5 minus 1, which is equal to 8. This equals 1. So 5 minus 1 is 4. You have 2 to the A minus 1. 5 to the C minus 1 is equal to 2, because 8 divided by 4 is 2. This is going to look silly, but 2 is equal to 2 to the power of 1 times 5 to the power of 0. Compare these two together, and you have A is equal to 2 and C is equal to 1. Consider back to n. A is 2 and C is 1. You have n is equal to 20. B of 20 is equal to 8. I already confirmed it. All right. There's 2 more cases left. I ran out of space, so I'm just gonna like, because you sort of get the idea. So like case 7 is when n is equal to 3 to the A times 5 to the C. If you go through this, you're gonna get n equals 15 and phi of 15 equals 8. And the last case is if n equals, wait, sorry, 3 to the B. Sorry, I made a mistake there. 2 to the A, 3 to the B times 5 to the C. And when you work it out, you get n equals 30, and phi of 30 is equal to 8. So then your final solutions will be n is equal to 15, 16, 20, 24, and 30. And yeah, so this is your final solution. Let's yeah, so that's pretty much how it goes. That was longer than I expected, and I used up the whole screen. So let's I will give you guys some practice problems to try. Find all n such that b of n is equal to 6. And I'm just going to give you the answers this time. N is equal to 7, 14, 9, and 18. I didn't do that in order. But yeah, these are the 4 solutions when you do the phi of n is equal to 6. Using everything I taught you, I'm going to give you a few steps along the way. You should have n equals 2 to the A, 3 to the B, and 7 to the C, where A, B, and C are all positive integers. Find, here, that was the first question. Find all n such that phi of n is 24. Try this one. This one's a little tedious. I suggest you be smart with your calculations on this one. It's quite long, but once you get this one, you're definitely going to get this one. I want to guide you. So when you do this one correctly, you should have n equals 35, 39, 45. There's 10 solutions. 45, 52, 56, 70, 72, 78, 84, and 90. Those are the 10 solutions for all phi of n, all natural numbers n, such that phi of n is equal to 24. And here's the final one. This one's a little trickier, but I really recommend you try it. Find all n, e, n such that 3 phi of n is equal to n. I'm not going to write the solution, show you the solution for this one. You can write it down in the comments. Yeah. But yeah, that's all I have for this video. Thank you guys very much for watching. We'll see you next time.